Let's move on to the next session, which is a fireside chat on ZK-VM security that will explore the unique security aspects of ZK virtual machines. And for that, I'd like to invite Jon Stephens, who is the co-founder and CEO at Veridise, and he will be accompanied by Rami Khalil, who is a senior blockchain protocol engineer at RISC Zero. So over to you, gentlemen.
Great. Thank you. Oh, good. We have a timer here. We've had similar discussions, and they've tended to go on for a while, so this is very helpful. But as mentioned, I'm Jon. I'm with Veridise, and we have Rami.
Yep, I'm Rami Khalil. I'm with RISC Zero.
And so we're going to be talking about ZK-VMs and a little bit about the security of ZK-VMs and how they could be useful to you. So why don't we start by just going through what is a ZK-VM?
Well, a ZK-VM is basically a generalization of ZK proving. Instead of writing circuits, you would write programs that would get interpreted by a circuit that can execute RISC-V instructions. So you don't have to worry about writing circom or writing complicated circuits. You would write whatever you want in your favorite programming language, and you just compile that down to RISC-V, and the VM would give you a ZK proof of execution. Okay.
Right. So, they've got a much better development experience because you're not writing this domain-specific language. You just write whatever language you want, like Rust. And so, as people are thinking about ZK-VMs, and since we're currently here with a lot of people who think about AppChains and stuff like that, how could a ZK-VM help them?
Well, what you would spend possibly a few months trying to develop as a circuit, you could do over the weekend as a project in a ZK-VM, right? Because you're just writing a general purpose language like Rust, like you mentioned, and you can use your favorite libraries to do that. You don't have to start from scratch and specify everything as a very hard to parse circuit.
So if I am writing an AppChain, how can I use ZK? Would I have to put my entire rollup inside a ZK circuit, or are there other ways that I might be able to use it?
You can use ZK wherever you can run the verifier. So the verifier for the proofs is something that is very light to run. We have a verifier that works in the EVM conveniently, and also for the SVM. So wherever you can run the verifier, even your fridge, you can verify ZK proofs. So your rollup doesn't have to be a full ZK rollup to make use of the ZK-VM. It just has to support the verifier.
Can you give an example of that?
An example of where the verification is?
No, an example of how someone might integrate a ZK-VM in other locations, like the Kailua application that you guys have put out.
Well, Kailua would basically enshrine your rollup in ZK or be used for fault proofs. Right? Kailua is something that we've built for proving fraud. So if you've deployed an AppChain, for example, and you want to secure that AppChain with ZK, you can use Kailua to either fully prove its execution in ZK or optimistically run it with fault proofs backed by Kailua using ZK.
And what benefits would it give you if you, for example, used ZK in order to generate these fault proofs?
So Kailua is very unique in that it can help you defend yourself against an adversary who might have 1 million ether to burn to attack your chain. Right? It is the only optimistic fault-proof system that can withstand this attack today.
Very cool. So you've already touched on this a little bit, but can you talk a little bit about kind of the additional security guarantees that you might be able to get by integrating with a ZK-VM? So if you're concerned about security and you have an AppChain that's maybe optimistic or even an L1 based off of consensus, what does switching to execution in a ZK-VM give you? What additional security guarantees does it give you? And then are there any trust assumptions that you need to be aware of?
So the nice guarantees you get is that execution, you get a guarantee on the integrity of the execution. So whatever the proof says the output of a program is, you know that it is the correct output based on the input. Another guarantee is privacy on the input. So you do the RISC Zero VM actually gives you ZK guarantees where the proof doesn't reveal anything about the input that is not revealed by the output itself. Right? The additional trust assumptions that you introduce are the cryptographic assumptions for the ZK VM itself. If you're only using the start proofs, then you have very minimal assumptions there. If you're also using the on-chain verifier, which is snark-based, then you have a bit more assumptions there for the snark verification, right? And also you're assuming that our great auditors at Veridise have done very good work looking at the security of the ZK-VM itself, which they have. I'm sure you can touch upon that.
Yeah, I can touch on that really quickly. So, one important thing about a ZK-VM is the fact that when building on a ZK-VM, you're basically trusting that the ZK-VM is implemented correctly and that, as Rami already mentioned, that the cryptography is sound. And so, at Veridise, we spent a lot of time looking at ZK circuits, and we not only audited properties or audited the ZK-VM implementation from RISC Zero, but we've also employed methods like formal verification in order to verify that certain properties hold within that ZK-VM to make sure that you do have a smaller trust surface when operating on a ZK-VM, because you know that in the case of the formal verification that we did, that is deterministic, but hopefully in the near future also that it actually implements the RISC-V specification. So that's a little bit on the security side, but another thing that has kind of come up, that came up earlier today and that has come up several times has to do with the cost of a ZK-VM application, and specifically executing that ZK-VM application. Can you talk a little bit about how someone might go about proving something expensive or an expensive ZK-VM?
So cost is something that has been going down rapidly with ZK-VM proving. We are at a stage where we can prove most transactions at a fraction of a cent in proving costs, and that is if you use AWS instances. So if you leave AWS and you run your own, you automatically reduced your cost to a third of that fraction of a cent. So we've honestly stopped worrying about expenses for proving ZK-VM execution. It's already pretty good enough for a lot of things, and it's going to go down drastically. Every month you see someone's 2x, 3x faster, and we're pretty optimistic about the roadmap for efficiency as well, or performance in general, being much faster, not just much cheaper this year. Someone was speculating it might be a few more, but it's happening much faster.
So if I wanted to build something on a ZK-VM, does that mean that I would have to run the prover and produce those proofs, or is there anything that would help me?
No, you can surely delegate the proof computation to a third party or to a decentralized proving network such as Boundless, our decentralized proving protocol. But you have to be careful that your computation, of course, doesn't involve any private input that would get revealed to the prover. That's the only caveat. But you can be sure that you will get a proof, because Boundless does provide a good liveness guarantee for proving if you're able to land your proof request at an appropriate price for the provers. Boundless is not going to get in your way. It's not something that is exclusive to one chain or the other. Boundless is something that is a protocol that will be available to any chain that can run it. And even if it is not on the chain that you're developing on or running on, you can always request proofs from one chain and use them in another chain.
Can you talk a little bit more about how Boundless provides some of those guarantees? Because you can imagine there being some fairly easy cases where someone might be able to either produce a proof that, or fail to produce a proof and without any good reason, like say the prover just took too long, or that a prover just kind of runs away with the money. So how are you providing any sort of liveness guarantees here?
That's a great question. So when you seek a proof on Boundless, you essentially start a reverse Dutch auction that the provers have to participate in as bidders to satisfy your proof request. So you can see that the provers actually compete to be the first to bid for your proof. to be the first to satisfy your proof. And that guarantees that you get the best price. So once the prover is selected as the one to satisfy your proof, they actually have to lock up collateral that would get appropriated in case they don't satisfy your proof within the time limit that you've specified. So they commit to satisfying your proof. And the incentives there basically are set up in such a way that if the first prover doesn't satisfy your proof on time, then there's actually more money available to further incentivize your proof on the second round and on the third round, and also the collateral that would be required to get locked up. To keep delaying your proof indefinitely, you would just become unrealistic, essentially, while the incentive to satisfy your proof or the payment for it keeps increasing. That's one way we're doing it. Another way involves incentivization on using a special cryptographic primitive that we will be releasing with the second version of our circuit that will give very unique incentives to participate in proving unboundless.
Okay. Okay. And what about protections for the prover as well? Because you mentioned that the prover has to fulfill a proof within a certain amount of time. So that necessarily means the prover has to have an accurate model of how long it will take in order to produce a certain proof. But since they're getting in random computations, that might not be very easy to do. So do you have additional protections for provers in case there's people here that want to participate in your network as a prover?
So as a prover, it's very cheap to pre-flight the proving or pre-flight the execution that will be proven. And once you have done that, you get a cycle count that's required to satisfy your proof. So it's very efficient to just monitor the boundless network for all the incoming requests, see how many cycles each of them will actually require locally to be computed, so you don't take the seeker's word for it. And be sure that based on your known local proving power, you would be able to satisfy this on time. So it's all configurable and very transparent and reliable.
Okay, cool. So we're running a little bit low on time. So maybe let's just revisit how someone might be able to use RISC Zero. So you guys have been working on setting up some, ZK-VM applications yourselves and making those available for other people to build on. So can you give a little bit of information about some of the resources that you guys already have?
We've made some pretty useful tools that streamline the development process for people building apps using ZK, one of which is Steel, which is a library that allows you to verifiably query on-chain information in your ZK application. We've seen people reduce costs from 10 billion gas, as an example, with some partners, to only $10 of proving in a few billion cycles. And things that are not just expensive, but otherwise infeasible, like 10 billion gas is quite a number. You'd make it very, very feasible, which is the goal, to make log space essentially boundless.
Yeah, I see what you did there. So I guess since we still have a little bit more time, what's next for RISC Zero? Is there anything that you guys are currently working on beyond boundless that will continue to provide more efficiency or easier use?
We're very excited about our performance roadmap. So we have an exclusive deal with the team behind Veridise to, definitely accelerate proving on the RISC Zero ZK-VM by about 30x, as we've measured so far. And on the software side, we also have many exciting developments for 2x, 3x, 4x. We have a lot of x multiplications coming up for performance, and these things happen quite fast, honestly. So from one week to the other, you should be rerunning the benchmarks.
All right, so multiples coming up, so then, yeah. All right, that's great. Okay, I think we are out of time, so I guess we'll go ahead and end there. Thanks for joining us.
Thank you so much, Jon. Great to be here.
Yeah, thank you so much, Jon and Rami.